Welcome back, my dear friends. A very good morning, good afternoon, good evening to all of you. And this is the data analysis and decision making course, which is DADM 1 course under the NPTEL MOOC series lectures. And we are in the 39th lecture. That means we are going to complete with another one, complete the 8th week. And you know, this total course is for 12 weeks. Which is about 30 hours. We will have 60 lectures, and each week we have 5 lectures, each being of half an hour. And I am Raghunandan Sengupta from the IME department, IIT Kanpur. So, we were discussing about principal component analysis, and the main idea about principal component analysis was that you have a set of random variables x1 to xp, and they are not independent. That is what I want to highlight from the beginning. And we want to find out the relationship structure of what is their total out of this p, what is the total number of such variables which are there, which will give us the maximum amount of relationship or the effects which can be found out by a linear combination of them. Now, this linear part is very important to understand, because as we said, as we mentioned, that we will consider the linear combinations of this x1 to xp at each stage, and basically combine them in such a way that the groups of the linear combinations would be orthogonal to each other. Point 1. Point number 2, also we said that we will consider only the standardized form, because the units of this x1 to xp, if they are different, then scaling would be affected. So, we would not consider the units to be quite different, in the sense that scaling factor is assumed not to be there, and we will consider the standard form. Now, our main aim is, if you remember, which I did mention about few seconds before, and I did harp on that fact in the 30th lecture when I was conducting it, the concept of linear combination should be such that they would be orthogonal to each other in those sets. In the sets, the first set of the linear combination would be orthogonal to the second set would be orthogonal to the third set, and obviously we will form the third set in such a way that it will be automatically linear combination of the first set. So, if when you go to the fourth set, first is linear to second, second is linear to first is orthogonal to second, second is orthogonal to third, third is orthogonal to fourth, and obviously it would mean that all of them, fourth would be orthogonal to first, and all of them would be orthogonal to each other. Now, later on I did show in the pictorial form that how it could be done, that considering it is only possible to show pictorially in a 3-dimensional case, that if you have x1 and x2, which is p is equal to 2, and there was x3 also. So, we want to basically combine them in such a way, the principal component 1, then 2, then 3, obviously we can consider 3 principal components, which would be combined by the linear combination of x1, x2, x3, they would be independent. Now, further on I mentioned, and which was very important, is that the concept of eigenvalues and eigenvectors will be used, because the eigenvalues and eigenvectors, which are basically orthogonal to each other, would give us the background of how we are going to basically conduct the principal component analysis concepts. Now, given the eigenvalues and the eigenvectors, we want to basically combine them. So, y1, then y2, then y3, then y4 till yp, considering there are x1 to xp. So, these would be the principal components which are basically being formed. These means y1 to yp are being formed in such a way that they are orthogonal to each other, and we will basically utilize the concept which I just mentioned, the eigenvalues eigenvectors concept will be utilized in order to find out those principal components accordingly. So, in the problem which I did not finish in the last class, I will continue discussing that. Now, if you remember, we had mentioned that we can find out the components PC1, PC2, PC3 in the way where we multiply the eigenvalues and eigenvectors corresponding to the fact that each rows and columns would be multiplied by the corresponding x1, x2, x3 and so on and so forth. So, this is what we are doing. So, what we had actually So, we had, I will just write it down. So, this less space, but please pay attention, you will understand. So, the eigenvalues eigenvectors are given, consider that 3, and these are the x's x1, x2, x3. Now, obviously, they are normalized, that means x1 would from x1 we will subtract the mean value of x1, from x2 we will subtract the mean value of x2, from x3 we will subtract the mean value of x3. So, once we have this, so the first value x1 will be multiplied by the corresponding value here, which is here, multiplied by x1. The second value for the would be multiplied by x2, the third value would be multiplied by the value 3. So, these are the values. So, if I consider this is the first value which is here, then we have the second value, and we have the third value. Now, remember here they are normalized. So, obviously, the second part being this one, second part of the first, the second part of the second, second part of the third. So, this value of 2, which I am not going to highlight anymore, the value of 3 and value of 2.5 are the respective mean values of x1, x2 and x3. Similarly, when I go to find out y2 again, so let me delete it. Would be, so I will delete this. So, first row is gone. Gone means it has been already taken care of through the calculation. The y2 would be this multiplied by x1 minus mu 1 the second value of the vector multiplied by x2 minus mu 2 and the third value of the vector of the second vector multiplied by x3 minus mu 3. So, these values would be here accordingly. I will just highlight it in order to make things. So, the first value would be this, the second value is this, the third value is this. Now, come to the last row and corresponding to y3. So, again first element of third eigenvector multiplied by x1 minus mu 1, second value of the third eigenvector multiplied by x2 minus mu 2 and third value of the third eigenvector multiplied by x3 minus mu 3. So, what are those values in order to find out y3? So, they are the first set of values, because this 2 is coming, as I am again repeating it, because as you are normalize it, and this 2 value is the mu 1. This 3 is coming because 3 is the mean value of x 2, which is mu 2. And this 2.5 is coming because the mean value of x 3, which is mu 3. So, once we do the calculation, so I will remove this. So, these would give me y 1, y 2 and y 3, which are orthogonal to each other. We will prove that, do not worry, we will prove that y 1, y 2, y 3, which is principal component 1, principal component 2, principal component 3. They are orthogonal, we will prove that, take that into consideration. We will also take that into other thing into consideration, which is important, is that the variability which we are going to prove for and find out for y 1, y 2 and y 3 would be in the descending order, with the variability coming out by the combination to find out y 1 being the highest, then y 2 would be the second, y 3 would be the third, and so on and so forth. For in this case, we have 3 random variables, obviously, hence there would be only y 1, y 2, y 3. Now, I want to double check. So, what I mentioned just at the fag end of the last slides, I am going to verify all the important facts. So, that will become clearer to you. So, way of double checking whether the principal component method transformations are correct is to calculate the sum of the squares of delta 1, delta 2, delta 3, considering there are 3 random variables for each of the eigenvalues which you have already found out. So, those eigenvalues were lambda 1, lambda 2, lambda 3. It is very intuitive to note that each of these variables which we have should basically add up to equal to 1, because that was basically the fact what we are doing. So, if you remember what we are trying to do it for the first case, when we want to find out y 1, we need to basically maximize the variability of the first one with respect to the fact that the sum of the constraints would be that the sum of the squares of the delta 1 square plus delta 2 square plus delta 3 square corresponding to y 1 should add up to 1. Once the variability is taken care for the first case, then we go to the second optimization, second stage optimization. Second, they are independent of each other in the sense the optimizations would definitely depend, the second one will definitely depend on the answer of the first, but in case we want to basically consider them as optimization problems, they are standalone problems. So, we will try to basically now maximize the variability corresponding to y 2, that means summation of delta 1 into x 1 plus delta 2 into x 2 plus delta 3 into x 3 would be maximized subject to the case that summation of delta 1 square plus delta 2 square plus delta 3 square is equal to 1. So, these delta 1, delta 2, delta 3 are corresponding to the second set, which is y 2. So, once that is done, then we go to the third stage of optimization, which is again independent. We will try to maximize the variability corresponding to y 3 such that delta 1 into x 1 plus delta 2 into x 2 plus delta 3 into x 3 would be maximized, the variability for that, and we will also see that the subject to some conditions would be summation of delta 1 square plus delta 2 square plus delta 3 square is equal to 1. Now, again these delta 1, delta 2, delta 3 are for y 3. So, technically what I am trying to say is that the first time optimization, those were delta 1 1 plus then delta 1 2 and delta 1 3. So, the first one is corresponding to the first stage, which is y 1, and the second suffix 1 2 3 are corresponding to x 1, x 2, x 3. Then we come to the maximization of the variability for the second, which is for y 2. Those deltas would be delta 2 1, delta 2 2, delta 2 3. So, the first suffix 2 would be corresponding to y 2, and the second suffix 1 2 3 would be corresponding to x 1, x 2, x 3. Then we go, when we go to the third case, it will be basically summation of, as I mentioned, summation of delta 1 square plus delta 2 square, delta 3 square. So, actually these delta 1 1, delta 2, delta 3 are actually delta 3 1, then delta 3 2 and delta 3 3. So, these suffixes which I mentioned 3 1, 3 2, 3 3, the first suffix would basically corresponding to y 3, and the second suffix 1 2 3 would basically corresponding to x 1, x 2, x 3. So, this is what we will have. So, there would be delta 1 1, delta 1 2, delta 1 3 corresponding to y1, the principal component 1. Then we will have delta 2 1, delta 2 2, delta 2 3, which is corresponding to principal component 2. Then we will have delta 3 1, delta 3 2, delta 3 3, which will be corresponding to the principal component 3, which is y3, and you can go on accordingly. So, again I will read: a way of double checking whether the principal component transformations are correct at each stage is to calculate the sum of the squares of delta 1 square plus delta 2 square plus delta 3 square at each stage. It is very intuitive to note that it will be true that they are 1. So, let us consider this is basically the values of delta 1 square, delta 2 square corresponding to, let me highlight it in a different way, so it will be easy for us to understand. So, would be this square, we will find out 0.3697 will be this one, 0.32 will be this one. So, square of them would give of 1, which is true. Second case, again square of them addition is 1, which is true. Again, when we add up this square of the deltas, add them up, it is equal to 1. So, it proves that the principal component, based on the fact that we have been able to break this principal component in the direction of the eigenvalues, is the right method. So, that part is done. Second part would be obviously the question, if you remember, I mentioned whether the variabilities are in descending order as it should be, because the first case of the variability we want to take out the maximum variability corresponding to PC1, then the next level of variability would be corresponding to PC2, and so on and so forth. So, we will come to that also. Another method to double check is to find the variances of y and we will check that the variability of y1, y2, y3 would be that in that order as already decided. So, variability of y, so what was basically y? So, y1 was equal to delta x1. So, I should be using 1 1. So, 1 2, 1 3. So, I want to find out the variability of that. So, variability variance would be delta 1 1 square, which is here, good. Then variance of x1, which is already known to us from the table, if you remember, the variance covariance matrix of x. Then we going to go to delta 1 2 whole square, so which will be equal to this. So, I'll just I'm marking those values, so I'm going a little bit slow, so you can check as I do it. Variance of x2, which would also be from the covariance matrix. Then delta 1 3 square would be this value multiplied by variability of x3. Now, what we will have? We will have basically the covariance values. So, they would be, they are symmetric. So, hence there would be 2 values corresponding to 1 2, 1 3, then 2 3. So, 1 2 values would be covariance of x1 x2 is given, and we will basically have the corresponding the values of delta 1 2 and delta 2 1, which we will have. So, this is the values. Then when we go to covariance of 2 3, it will be multiplied by the corresponding values Then we go to covariance of 1, 3. It will again be multiplied by the corresponding values. So, technically delta 1, 1. So, that will come once here, second time when we are trying to find out corresponding to covariance of x 1, 2, and third time it will come when you are trying to find out the covariance of 1 and 3. So, let us check. Yes, it is there. So, delta 1, 1 is taken care. Now, let us come to delta 1, 2. Delta 1, 2 would be corresponding to this value. So, that is for the variance of 2, then it will come into the variance of 1 and 2, and it will also come into the variance of 2 and 3. So, let us check. Yes, it is there. Now, we will come to delta 1, 3. So, that will again appear thrice. So, let us take the green color. So, that will be minus. This is a minus sign if you remember for the eigenvector. So, let us come there in the variance of 3, then it will come into the variance of 1, 3. So, variance of 1, 3 is here, variance and 2, 3 is also here. So, that takes care of all the delta values. So, we find out the variances. So, that would actually be equal to the first eigenvectors, because that is basically maximum amount of variance which we will trying to basically find out. So, that is actually equal to and that proves the second point corresponding to y 1. The first one was basically variability in the decreasing order, second one was orthogonality. So, we have taken care the first part and the second part, first part for all of them, second part for the first y 1. So, let us come to y 2. Again you will basically have, I will write down the formula because the calculations would be simple. So, it will be delta for the first for variability of y. So, it will be, so let me write down y first. Let me write down y here. So, variabilities is coming 2 1 square. So, I will write down the principal values along the variance and covariance. So, this would be considered first. So, this is, so the first value is taken care. Second value is taken care. Third value is taken care. Now, I need to take care of the covariances. So, there is one value here and a one value here. That will be twice into delta 1, 2. So, that would, wait, just. So, they would be basically, I would not give the suffix now, wait. So, I should have basically written as, so this will be delta should be delta 1 1 for the first case. So, how should I wait, just wait, because the nomenclature may get a little bit confusing. So, I want to basically settle it out. So, this is for the second stage, that is y 2. I mention it 1 1, mention it. So these would be for the first one, for the second one, for the third one, and corresponding to the of the diagonal elements. So I will remove these suffixes, so it will be easy for me to denote. It will be delta 1 which is here, delta which is second case, delta is the third case. Then I will have the values so I will basically multiply these values. So these are the values which I am multiplying by the covariance of x1, x2. Then it will be twice into these values multiplied. So it will basically, and one would be so I will take this here. So 1, okay, so this value, sorry, this won't come. This won't come. This is the third value taken care, and the fourth value taken care. So this would be twice of. These are not symmetric, remember. So once we have this for y2, we find out the value of variance of y2, this second case, and then the variance of y3. So based on that, we will proceed step by step to find out the variability and the eigenvectors, which would basically come out from the corresponding case of the variance of y1, y2, y3. So this is a little bit involved problem, I understand. Solving it using the same problem, using a simple eigenvalues, eigenvectors, and then trying to find out the combinations to find out y1, y2, y3. Then two things: find out the variability and the variance and the orthogonality. So once you have done all these three things, you are rest assured the principal component method which you are trying to follow gives you the actual result which is required. But remember again that the linearity of the axis is important, and the standard form it is utilized, where the units of the x1, x2, x3 till xp are not affecting our calculation. So with this I will end the 39th lecture and continue discussing more about the multivariate statistics in the subsequent classes. Have a nice day and thank you very much.